on?
Yes.
Okay, we're recording. Hi.
Hello.
We don't
Yeah,
have,
it is.
We don't have a teacher.
We're doing our best.
We're doing our best.
We miss you.
Okay.
All right, it's working.
Yeah.
All right.
Yeah, I'm coming. Oh, okay.
Hi.
No problem.
I guess
We think so.
we think so.
Yeah.
Are we supposed to be recording to the cloud or to the computer? Okay.
So we're
We're recording. And Herbie, you want 6 minute like thing? Do you want me to like tell you when it's at 6 minutes?
And then 7.
Yeah, sure.
Okay. Do you want to do 5 too?
Okay, sure. Oh, I'll just like I can count you down. Yeah.
That'd be great. But at least starting at 5.
Yeah.
All right. Hello, everyone. I'm Herbie, and this is my presentation on the physics of Wii Remotes. But before we get into the fun physics behind it, we need to get some like cultural and historical context here. Okay, so let's go back in time. It is early to mid 2005, and half the juniors in this room don't exist yet. All right. Generation 6 of video game consoles, the PS2, the Xbox, and the GameCube, have been a massive success. They successfully made that massive leap from primarily 2-dimensional games to primarily 3-dimensional games. And as all the video game executives sit in their rooms around the tables, they're asking themselves, where do we go from here? Because the world is in 3D and our video games in 3D, and there's no real obvious like next progression. So what Microsoft and Sony end up doing is they sort of go, oh, well, we'll increase the specs, we'll have better graphics and more computational power. But what Nintendo president Satoru Iwata at the time said, which was extremely new and innovative, was he said, let's not do that. I don't want to create a new console that's just the exact same as the previous one, but with better specs. I want to do something revolutionary. And so we ended up with the Wii. Okay. Now, for those of you, I'm going to give a little bit of a refresher. What was so special about the Wii is for the first time on a large, successful scale, you could have motion sensing capabilities to put inputs into your video game. So you can sort of waggle your Wii remote around and it'll make your little character swing a tennis racket around or something like that. Now, there are other fun things as well, like making your own characters. And it came with really enduring games, like Mario Kart Wii and Golden Balls. Have you got what it takes to take the lots? So now I've been that little refresher. Who here remembers the Wii? You can raise your hands. Oh, great, you're all awake. Who here remembers it fondly? Who had good times? Now, who here knows how the remote worked? That's what I thought. All right. I'm going to teach you all that today. Okay, so let's see the physics behind this Wii remote. There are 3 primary components of the Wii that I'd like to explain to you today. There's the MEMS sensor, the 3-axis accelerometer, and both those are inside your remote. And there's the infrared sensor bar, which you sort of set in front of your TV, which allows you to sort of point at the TV and use your cursor. And then finally, there's a Wi-Fi system, so the wireless remote can communicate with the console. But I won't be getting into that too much. Okay, so first is the MEMS sensor. For those of you who are wondering, MEMS stands for micro electromechanical systems. And essentially what that means is everything I'm saying can be done on a really large macro scale, but in this case, will be done on a really small micro scale, so it can fit on a circuit board. Now, what it does is it detects if the Wii remote is at some sort of angle, it could be like this or like that, and then it quantifies the degree of that angle and outputs it as an electrical charge. So how does that work from a physics standpoint? Well, we basically have a small little compartment inside of our Wii remote with 2 negatively charged capacitors on either side and an electron flow going in between them. Now you suspend a positively charged conductor in between the 2, so it's free hanging and it's able to rotate. Essentially what happens is as you rotate your Wii remotes, because that's freely suspended positively charged conductor will always point to the center of gravity, the degree angle of the rotation is equal to the degree angle of here. And you guys are probably familiar with that from when we used to do word problems where you have like a hill and a ball rolling down it. It was the same principle there. And so what that means is we can then measure, hopefully this is like something that you all know, but if you move a positively charged object through an electric field, what you end up getting is a change in electrical potential. And what these capacitors can do, that's what capacitors do, is they record changes in electrical potential and output them as an electric charge. So essentially, as this shifts through the compartment, it creates a change in electrical potential, which the capacitors then output for the video game to use. Next up, we have 3-axis accelerometers. Now, whereas the first thing, the MEMS sensor detected rotation like this, or sort of tilting of the remote, this measures acceleration of the remote as you swing it around. And it's the same principle where ultimately you're going to be having an electron field or flow with a positively charged object moving through it. But in this case, instead of it being free hanging, it's going to be caused by this cool system of springs and a dampener. So to explain that, we have to sort of remember all the way back to the beginning of the year when we were learning about springs and elastic motion and stuff like that, and recall Hooke's law, which says that there's a linear relationship between the distance that a spring is compressed or stretched and the force that is applied on it. So if we apply one mass, and of course acceleration is just gravity here, we'll have X centimeters of stretch. And if you apply double the amount of mass but the same amount of acceleration, so basically doubling the force applied, it doubles the distance of the stretching. And so that's Hooke's law right there. It's F equals negative K of X, where K is some sort of spring constant, which is dependent on the spring, how stretchy or not stretchy it is. Now, what basically happens is, as you move your Wii remotes, because of Newton's first law, we have this proof mass that is freely hanging. So because of Newton's first law, it won't move as the remote starts to move. There's no actual force being applied to it. It's freely able to move in the inside. As you move the remotes, this spring will come in contact with the proof mass. Okay, thank you. And it'll begin to apply force, but it won't be enough to push the mass just yet. The spring will compress and compress. And as that distance of compression increases, Kx increases, so the force it applies increases. That's just Hooke's law. And eventually it'll compress and compress and compress until the force it's applying is enough that it doesn't compress anymore, and instead pushes the object. And at that point, you have the outer shell of the Wii remote and the mass and the spring all moving in tandem. And the spring will be at a certain degree of squeeziness and won't be changing. At that point, by having a positively charged conductor at the end of the spring inside an electrical field, you can know how far in the electric field it's shifted, which will tell you how much force is being applied, if that makes sense to everyone. And so then you can quantify that as an electric charge and output that for the game. And so that's essentially how accelerometers work. And just as a cool aside, it's the exact same principle in your inner ear. When you sense movement like that, you have these little basically rocks that they call ear rocks in your inner ear that are called calcium carbonate otoliths. And basically they're able to freely move inside your ear, and you have hairs, inner ear hairs, as your spring. So it's the same sort of idea there. Now, a quiz question before I begin to wrap this up. If I have my Wii remote and I put it flat on a table or on the floor, what will the accelerometer give out? Like what number? Do you have any guesses? You can sort of shout it out. 0. That's a good guess. You're wrong. Because of course gravity is always being applied to the object, so it's going to be counterbalancing gravity, and the y-axis one is going to have 9.81 meters per second up. Now the very last thing is the infrared sensor. This is a bit of a misnomer because it's not actually a sensor at all. Instead, it's just a bar with 2 infrared emitting lights on either end, and you know that you can replace it with candles and get the same result. Then you have an infrared sensor at the tip of your remote, which detects the interference patterns of those 2 diodes. So as you can see here, when they're completely in sync, they're both up. You have twice the amount of total wavelength, and when they're completely opposite to each other, meaning that one is at the peak while the other at the trough, this combined line, this represents both of them at once, becomes really short. And so you end up getting this pattern as the 2 diodes mix of really high and really low, and this detects that, thank you, and it quantifies it as an electric charge, which can be used to sort of point your Wii remote at the TV and use your cursor. So to summarize, we went through MEMS sensors, accelerometers, and then finally a little bit of interference patterns, some light wave movement. And that's my presentation. Those are the sources. Thank you very much for listening. Ooh, questions? Yes.
So for all of the measurements that it's taking, like whenever, like the accelerator thing, whenever you're using it, it's always both a measure. Like, does it take an X and a Y component? Like,
yeah. So for example, for the accelerometer, you quite literally, I showed you that setup with a spring that sort of gets compressed. There are quite literally 3 of them, one on each axis. So that as you move it, let's say like that, which is in multiple axes at once, you'll get 3 different measurements in each accelerometer. And that combines to sort of quantify the movement as it's detected. Yes.
This is going to be a very poorly phrased question. I don't know how to phrase it, but for the I've forgotten what it's called, the sensor that swings to sense the tilt.
Yeah.
So the bar in the middle is positively charged. How does that allow it to detect? Like, how does the computer then get those signals and know what's going on?
Yeah, so if I'm honest, I don't actually know how capacitors work because we never learned it, but like I suppose it's a pretty basic part of circuitry where there's just this when you look at a photo of it online, it's like these two sort of bars. It's a little bit like when you look at a voltmeter or something, but it has a different function. And it essentially somehow or other detects a difference in electrical potential between the first bar and the second bar. And so as that positively charged thing shifts, it doesn't need to know where it is. It just needs to know how that shift changes electrical potential, which is then measured. Yeah.
You described the evolution, the invention of the Wii Remote as innovative. Did the technology used in the Wii Remote like become used in other consoles or?
Yeah, it's funny. That's an interesting question, right? Because the Wii was like the most widely sold console or home console of all time. And so you'd think we'd be having a million like motion sensing things all the time. And of course, the Switch has it. It has the same sort of stuff. And we had like Xbox 360, which is a different idea, but it was motion-based things. But right now, I think what it really comes down to is really temperamental and frustrating. You know, we've all played Wii Sports and gotten really pissed because it's not quite detecting us right. And I think as of right now, the technology is just not quite up to par, and that's why we don't see it as much, but it's only increasing. I mean, the Wii was in 2005, 2006. At the time, it was revolutionary. Now it's a little bit janky. But, you know, VR headsets and the little hand controllers use the same exact principles here, the same exact MEMS sensors and accelerometers, just sort of on a more, they're more accurate. Yeah.
This may be like a very silly question.
Yeah.
But how susceptible is like the Wii remote to like electrical interference? Like, let's say I'm in a thunderstorm and I'm just like waggling my Wii remote. If I get struck by lightning, well, I mean, okay, that's a bit dramatic, but like, yes, I would. But like, how would the Wii remote be affected?
That is an excellent question. I've researched thoroughly, as you can imagine. What I will say, I don't think it'd be any different than if you're using your phone, because ultimately all it's doing is communicating using like Wi-Fi to the console. So whatever happens to you when you're holding a phone and you get struck by lightning, it's the exact same thing there. And I'm sure you're familiar with that. So, yeah. Do you have another one, or is?
We're a little bit low on time.
All right, low on time. Okay, thank you all very much.
Don't worry.